So hey folks, we're going to do part two of the series solutions to differential equations section. And this is actually the last section we're going to cover in class for MA 301. This is the last topic. Then we'll do some review and have the final exam stuff, or review, next test, then the final exam review and that kind of thing. So this is the last topic that we're going to cover. Had we had more time, we would have also tied in concepts of solving differential equations that have periodic solutions. And we would have tied in Fourier series into this too. We're sort of running out of time. So there's a bit of a disconnect perhaps in your mind. We talked about series for a little bit, went to Fourier series, now we're doing series solutions. How does the Fourier fit? Because had things gone to plan, frankly, we would have then gone to Fourier series at the end and sort of all wrapped it up. Had I known we would have made it, we would have done series solutions of differential equations, and then Fourier series probably. But oh well, this is where we are. So the last time we talked about stuff, part one, we focused on linear first order equations. They were all basically kind of similar. We saw e to the x pop up a lot, and that was just because we were making sure things were simple. Again, had we had a text that was fuller, and things like that, we would have done more, and we were in person without wearing masks, all that kind of stuff. We would probably gone farther. Anyway, it got you the idea though of I can write out a series expansion of an unknown function. I can find its derivative with still now variables floating around, and then I can combine them in ways and then equate that to something that is known, and go from there. And so we're going to go into more complicated things. I was going to do more complex examples, but I didn't want to have a pun involved with that. So complicated examples. These aren't necessarily like nothing's really new here. We're just going more in depth, combining things in new ways, and you'll see what I mean with that as we do it. So here's our first example. Let's approximate a solution to y prime times y equals 1, where y of 0 is equal to 1. All right, so there's a multiplication there instead of like an addition subtraction. So as before, here's my series expansion of y a naught plus a1x plus a2 over 2x squared. It's that Taylor series idea where I have these n factorials and then some other coefficient there. And that means y prime is equal to a1, a2x plus a3 over 2x squared, a4 over 3 factorial x cubed, and things like that. Keeps on going. So with y prime times y, well, here's that y prime, dot, 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 times, and here's y. And that's all supposed to be equal to 1. But now we're going to apply the distributive property here. We're going to take a1 times all of this stuff, plus a2x times all of this stuff, plus, and keep on going. So we're going to get 4 of these things. Here's a1 times that whole thing. a1 times a naught plus a1 times a1x plus a1 times a2 over 2x squared plus a1 a3 over 3 factorial x cubed, so forth. Now here is a2x times everything. Here's a2x times a naught. Kind of put it a little bit out of order, but kind of made sense to put the x last. Here is a2x times a1x, so it's a2 a1x squared. And then a2x times a2 over 2x squared gives me an a2 over 2, sorry, a2 squared basically over 2x cubed. Then a2 over a2 times a3 over 3 factorial x to the fourth. And then you don't know this for sure right now. I just know where we're going in the future. I don't need anything more than a quartic. And that's not true all the time. It's just like for us right now, I'm not going to go beyond quartics just because it's enough terms to show that I know what I need to do to get going. And then again, technology can help us with this. We're not necessarily going to do this by hand all the time. And then you can expand things as far as you need to. So now a3 over 2x squared, factor that across. I have, so a3 over 2 a naught x squared. a3 over 2 times a1x times x squared gives me x cubed. Get this last term. And then lastly, a4 over 3 factorial x cubed times a naught gives me this term here. a4 over 3 factorial times x cubed times a1x gives me this term here. And again, I'm stopping at the quartic. So as these degrees go up, there's fewer things over here that I need to multiply with to get a quartic. So I have, what, 1, 2, 3, 4, 5 terms here, then 4, then 3, then 2. And I'm stopping. And I'm going to say combine like terms. So I only have, and I can compare across pages this way here, I only have one term that's a constant with no x's. That's a1 times a naught, or a naught a1. Then I have two terms here and here of things with x in it, a naught times a2 plus a1 squared times x. And then I have three terms that have squareds in them. So I have an a naught a3 divided by 2. That shows up with right here. And then I have an a1 times a2. And then I have an a1, a2 over 2. And I wrote them out separately. I can combine these. I wrote them out separately just so you can see that I had three places they come from. And then you can also tell there's a pattern here. Like these subscripts add up to 1. These subscripts will add up to 2. This is an a1 times a1. These subscripts will add up to 3, a naught a3, a1 a2, a2 a1, basically, or vice versa, a2 a1. So, and then now these subscripts will add up to 4, and there's 4 of them I can find here. There's one here, 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 and here, and then you add them up, and again, and that gives me, I'm sorry, that's the cubic part right here, 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 and here. And there's one more term that we could have gotten another quartic term had I done one more where the quartic was right here. So effectively, I really should have just stopped at the cubic, but I wanted to show you a little bit more where things came from. So anyway, so we're stopping here at the cubic. And all this is supposed to be equal to 1. Well, if that equals 1, well, this is a constant, so therefore this constant must be 1. And then there's no x stuff, there's no x squared stuff, there's no x cubed stuff over here, so this coefficient must be 0, this coefficient must be 0, this coefficient must be 0. So I have a naught a1 is 1, and then everything else, all these other coefficients add up to 0. And those look like complicated equations at first. There's just lots of variables floating around, but they're actually not that hard to deal with. Remember that we had the initial condition that told us that y of 0 is equal to 1. And if I go back to my original function, if y is equal to all of this and y of 0 is 1, so I plug in 0 for x, I'm left with a naught. That tells me a naught is 1. But if a naught is 1 and a naught times a1 is 1, that means a1 has to be 1. And now that I know a1 is 1 and a naught is 1, I can go into this equation here, and a2 is the only thing that I don't know, and it turns into a linear equation. Right now it's not linear, but when I know some of these variables, it turns into a linear equation. A2 is just -1. And now I know what a naught and a1 and a2 are. This again turns into a linear equation, and it's not hard to work through the algebra. A3 is equal to 3. And then finally, this last equation here, again, turns linear, and I can find a4 is equal to -15. Okay, so now I can find a4. And so back to my thing about worrying about quartics, I wanted to be able to get an equation that had an a4 in it. That's why I went down to, that's why I was able to stop right here. I got my first a4, and that's all I needed to do. So now I have what a naught, a1, a2, a3, a4 are. So our best, in this case, quartic approximation to this differential equation with this initial condition is, put them all together, a naught is 1, a1 is 1, a2 is -1, but I had an a2 over 2, so I get -1/2. And then I have a 15 here, I have a 3 here, so it's 3 over 3 factorial is the same thing as 1/2 x cubed. And then I can simplify this, but I didn't at first. -15 over 4 factorial, -15 over 24. You can simplify that to 5/8. So I get this equation here. All right. Turns out that the equation that I wrote you, the y prime times y equals 1, it's solvable by other methods. And I am a fan, oftentimes, of solving new problems where I can find the solution other ways. Then I can compare and say, did my new solution, did it actually make sense? So I haven't actually solved the problem. I have come up with a 4th degree polynomial that approximates the solution. And generally in real life, you don't have complete information, or you have things that are really hard. You're always going to settle for an approximation anyway. And so this seems like a fine place to stop it. Now let's just compare to see how good we have. So the original differential equation is solvable, where it's the square root of 1 plus 2x. Let's just confirm that real quick on the side. What's y prime? Well, rewrite it with a half power. Y prime is this. That's a times 2, not a 2x. That's a blah mark. which is just 1 over this. Oh, wait a minute. I multiply y times y prime, I get 1. Yeah. And then you plug in 0 for x, you get 1. So that works. So this is my solution. So then we could graph this function here with this quartic, and you would see that they're pretty similar to each other. So I wish I could graph stuff. You know what? I've been playing around recently with stuff online just because I was bored with the pandemic, and I found this cool program called Mathematica that you might be interested in. And so this top equation right here, in blue is the square root of 1 plus 2x. That's the true solution. And then in this other color, goldenrod, is my quartic. And sure enough, looking at that between -0.5 and 1 and +0.5, it does pretty good. And then something that we didn't talk about within class, but this polynomial, if you continue it on, actually is only going to be good. It's only going to be accurate between -1/2 and +1/2. No matter what we do, once we get past 1/2, it's going to start tailing off more and more. Or I should say, if I zoom in right there, you can see there's a gap there. And no matter what I do, I can squeeze that gap out of 1/2, but after 1/2, there's always going to be a gap there. So they called it the radius of convergence is 1/2. I was centered at the origin. That's where my initial condition is. That's where my series is centered around. And go plus or minus 1/2, I can't get anything. I won't get convergence outside of that interval. But the key is I did get a good solution, though, on that interval. All right, in the next video, we'll start talking about example 2, where we have a second order differential equation, y double prime. So stay tuned for that video.